We learned a lot about magnetism, but how does it work? What actually is magnetism? What causes it? Magnetism is derived from the motion of electrons. It's either the spin motion or the orbital motion of them around the nucleus. But when I say spin, I don't mean that it's spinning on an axis like this is shown. It actually spins in a much more complex way that we can't really conceptualize, but we know it behaves like it's spinning. We know a wire with a current running through it has a magnetic field around it because of the moving charged particles. So really, a loop of charged particles is very similar to the orbital motion that we showed before. When you just think of it as just one electron moving around, it becomes a sort of mini-magnet. This defines what we know as the magnetic moment of the electron due to its angular momentum. Understanding the magnetic moment of an electron due to its spin, however, is a little bit more complicated than the orbital. Because the electron spin doesn't obey classical physics, it is a part of quantum mechanics. No one has really figured out exactly why this spin creates the magnetic field, but what we do know about the magnetic field is how it behaves. The angular momentum of these electrons is actually quantized, which creates what acts as a north and south end for our mini-magnet. This was proven by the Stern-Gerlach experiment in 1922. The experiment was done by shooting a beam of electrons through a variable magnetic field. The magnetic field should have scattered the electrons randomly based on the random orientation of their magnetic fields. However, what ended up happening is that the electrons kind of sorted themselves into two spots. This meant that the electron's spin was quantized into two directions, spin up and spin down. But there isn't just one electron in an atom, there are many, and there are many atoms in a substance. So how do these all act as a group, and how does that affect its behavior as a magnet? You may remember from chemistry the Pauli exclusion principle, which states that no two atoms with the same spin can occupy the same suborbital, and that these suborbitals fill up with one of each spin and then can add in another electron. But this means that some elements have unpaired electrons in these suborbitals, which means that their spins add together, and these are the elements that we consider magnetic. These elements are located in the middle of an atom group where they don't have the full amount of their orbital filled. They have about half, so there are more unpaired electrons. However, you'll notice not every transition element that is in the middle of the group is magnetic. And we'll get into why this is later. There are certain elements that are much stronger magnets, and these are the rare earth metals. The rare earth metals have a unique structure that allows them to be more magnetized because their orbitals do not cancel. The orbital motion that we were talking about before, the orbital moment, does not cancel in these. And this is because that how the orbitals fill up. If you remember, the Aufbau principle from chemistry states that the 4f orbital will fill up before the 5d or 6p or 7s orbital. This means that towards the center of the atom, there will be more unpaired electrons. This provides a certain degree of shielding to the electrons, which allows them to be a stronger magnet. The 4f orbital also has the possibility for 7 unpaired electrons in comparison to the d orbital, which only allows for 5 unpaired electrons, which the transition metals were taking advantage of. Now, these magnets are very important when it comes to building things like laptops, computers, smartphones, and despite the name, they're actually not that rare to find. They only are rare to find isolated. They're usually found with other elements, and that's what makes them so hard to manufacture, is refining them into just the element, since this process does produce a lot of toxic waste. Now back to the other elements with unpaired electrons. Even though the atoms act as magnets, as a group they do not act as a magnet, and this is due to their temperature and structure. Most of these elements are paramagnetic, and that means that the electron spins do not line up. Instead, they're scattered randomly, and it doesn't really act as a magnet because of this. Some are ferromagnetic, and that means that their electrons are lined up into groups. The spins of them are lined up into little groups called domains. And whether a atom is in a ferromagnetic state or paramagnetic state depends on its Curie temperature. When an atom is below its Curie temperature, it acts as a ferromagnetic, and above, it acts as a paramagnetic. These are the temperatures for iron, cobalt, and nickel, and as you can see, their Curie temperatures are very high, which makes it easy for them to be in a ferromagnetic state at room temperature. Meanwhile, most other elements have much lower Curie temperatures, so in order to actually have them act as a ferromagnetic, they'd have to be cooled way down. And these are the only elements that have a Curie temperature above room temperature so that they can be observed as a ferromagnet. Now, there are some elements that are antiferromagnetic elements, and this means that the electron spins line up opposite to each other. And it does this because this is an energy state where that is more favorable to it because of its structure. An example of this is chromium. And antiferromagnetic, just like the Curie temperature, have a Néel temperature, and under this temperature, they act as a antiferromagnetic, and above it, they act as a paramagnetic atom. So you can see that atoms and magnetic fields are really easy to manipulate. Here I have a pair of scissors that is made out of steel and has iron in it. The scissors are not magnetic. I can't pick up these paper clips with it at all. But if I rub a magnet along it in one direction repeatedly, I can actually create a magnet from the scissors that weren't a magnet before just because of the material, and I'm lining up the magnetic domains. This can also be done by placing two magnets of opposite poles on two sides of a piece of metal and leaving that there for an extended period of time. This will also change the iron into a magnet because it'll be lining up the domains to each pole. Now you can see here that after I've done this, the scissors are able to pick up the paper clips because it is magnetized. So where does magnetism come from? The quantum mechanical properties of electrons that allow themselves to create a magnetic field, and the structure of an atom that can allow for the electron's magnetic field to be aligned in either in opposite directions, or in domains. And then the aligning of those domains to create a larger magnet that we are able to use for a variety of different things. There's still a lot we have left to learn about magnetism and how it works exactly, and that is going to be a pretty interesting chapter.